Alright, in this video I wanted to address the question of how do we evaluate the accuracy for the regression model. Now, when we say regression, I just want to remind you, recently we have switched to the discussion of data models where the target variable is numerical. So everything that we've done so far this semester was kind of revolving around categorical target. Well, not everything, but for the modeling piece. In the last couple of lectures we discussed two new models actually that allow making predictions when your target is numerical. The first one was regression tree, and the second one was the simple linear regression. And for both of these examples we have used the same data set for prices of Toyota Corolla. So in this video, which I hope will be relatively short, I wanted to discuss how do we evaluate accuracy of the regression model. So this set of slides I'm going to upload on Scholar. So first, let's kind of discuss classification models that we've done so far. So in the classification models, the target is categorical. We had a Titanic data set, we had data set about the bank offering customers personal loans, etc., etc. So in these cases, our target was pretty much always yes or no, categorical. So when we build a model, such as classification tree, the model will get the answer yes or no, either right or it will get it wrong. Simple as that. Okay. So for that reason, each time when we make a prediction, there were two possible outcomes. The model says yes, and the actuality is yes, so that's true positive. The model says no, and the reality is no, that's true negative. The model says yes, but actually it's a no, that's false positive, and the model says no, but actually it's a yes, that's false negatives. And from these outcomes, we were able to calculate 4 different measures. How well the model performs the prediction. That was accuracy, closely related measure, misclassification rate. Accuracy plus misclassification rate must give us 100%. And then there was sensitivity and specificity. So sensitivity, again, reminder, it applies when our categories, yes or no, for the target variable, they're not the same in terms of importance. When it's more important to predict yes as opposed to correctly predict no, then for the correctly predicted yes responses, the percentage of correctly predicted yes responses is called sensitivity. And for the secondary category, which is not that important, it's called specificity. Okay, so that was about the classification models. Now what happens with regression models that we just started? Well, problem is that target is not as simple as yes no. It's not categorical, but it's numerical. It's a number. We're predicting a number. So for example, if the actual price of the car is $12,000 in our model, whichever it is, it can be regression tree, it can be simple linear regression, it can be something else, the model predicts that the price is $11,500. Well, we clearly see that prediction is different from the actual, so therefore the model is wrong, right? Well, the fact is that your model will very rarely be exactly right on the target. In fact, if you will see that your prediction for the numerical target is exactly equal to the actual value of the numerical target, that can be considered as a lucky accident. Okay, so almost 100% of all your predictions will be off. So they will not be exactly equal to the actual values. So that means that our accuracy is going to be 0, pretty much, right? We're never right. Every time when we predict something, we get it wrong pretty much 100% of the time. Well, it just basically means that we cannot use the same measures as accuracy, misclassification rate, sensitivity, and specificity. We have to use something else. So how exactly do we measure the performance of the regression model? Well, if you already took BUSN 304 Operations Management, you studied the forecasting there. Forecasting is predicting the future. Okay. Well, what we're studying right now is predicting numerical target. So conceptually, it's the same. Most cases in operations management, when talking about forecasting, you predicted the future demand. You can predict anything really. You can predict the stock price. You can predict the temperature. You can predict anything else numerical. Or future demand. That's the most frequently predicted measure. And the first rule of forecasting is that no matter how hard you try to predict your demand, for example, 100% accurately, not going to happen. You will always get it wrong. That's the first rule of forecasting. No matter what you do, your forecast is going to be inaccurate. So it's going to be off, different from the actual. Now, what separates good models from the bad models is good models also get the forecast wrong, but they are closer to the actual values than the bad models. So therefore, our measure of accuracy should take into account, okay, I got the prediction wrong, but how close was I? Was it close enough, or was it too far away? So let's switch our attention back to the Corolla example with Corolla prices. So here is the table with a bunch of fake data, really. So about each car, we know a lot of different variables. So our target is the price. That's what we're trying to predict. And predictors are mileage, age of the car, what type of fuel it's using, and then there was something else in the file, something like color, is it metallic or not, transmission, is it mechanical or manual, how many doors, what was the car weight, etc., etc. So I just replaced them with dots here. Okay. So let's say I built some sort of the model. It can be regression tree, it can be simple linear regression, it can be something else. And I use that model to predict my car prices. You can see that in each case, for each car, here's my actual price, here's my forecasted price. They're different each time. So here, for example, forecasted is higher than the actual. So what we need to do is for each of the predictions, so for each of the data points in the data set, we have to calculate the error. The error is numerical value that tells you how far you're actual from the predicted. So this is the standard way how errors are calculated. The actual price minus the predicted value. So in this case, actual price 12,584, the predicted is 13,405, and if I subtract the price minus the predicted, then I'm going to get an error. In this case, error is negative because price is lower than the predicted, so I over predicted. My second car, the actual price was 16,145, the predicted was much lower actually, $13,032, and the difference is positive now these days. In this case, showing me that the I under predicted in this case. So my predicted forecasted price was lower than the actual price, and I can do that for each and every car. So I have a bunch of prices, the real prices, and for each actual price, what my model says the price will be, so predicted, and I'm going to calculate the errors. Okay. So, as we discussed after that, how do we evaluate the accuracy? Well, the closer my actual prices to the predicted values, the better the model. So in other words, my errors should be small. If errors are small, I have a good model. If errors are large, I have a bad model. So the standard ways how the accuracy is evaluated are right here on this slide. So they're pretty much the same as what is used for the demand forecast for operations management purposes, for example. So let's kind of discuss each and every one of them. In the previous slide, you can see that some errors are positive, some errors are negative. So one thing that what I can do is calculate the average error. That would be the most intuitive, natural thing to do. The problem is when I start adding up errors, my positive errors will compensate negative errors, so the result will be close to zero probably. And after that I'm going to say, wow, my model is great, the total error or average error is zero. Well, no, not really. What happened is, in a lot of cases you over forecasted, in a lot of cases you under forecasted, but when you added them together, that looked like you had no errors, which is not true. So therefore what we need to do is essentially eliminate the sign of an error. Error is an error. I can be over predicting, or I can be under predicting. Both of these outcomes are actually kind of bad. So therefore it doesn't really matter if the error is positive or negative. I'm going to convert everything to the positives. How can that be done? Well, one way to do it is calculate the absolute value of error, which actually shows me that here is the error in my slide, pun intended. Alright, so I have to, in order to calculate the mean absolute error, MAE, what you need to do is take all the errors, calculate their absolute value, and after that calculate the average. So add them together, divide by n. Or it's the same formula. Error is actual minus the forecasted. So you take all the errors, calculate the absolute values, add them together, divide by n. So mean absolute error. Also in the operations management, this measure was called MAD, not MAE, but MAD. D stands for deviation, mean absolute deviation. Okay, so this is one way how the errors are calculated. The performance of the regression model is estimated. Another measure is MSE, mean squared error. So one way how I can convert my errors from negatives to positive is absolute value. Another way is when I square the errors, if they were positive or negative, after squaring the error, they all become positive. And I do the same thing. Add together squared errors, divide by n. Oh, and this is just expanded formula. The actual minus the forecast for the same car is the error. I square it, add them together, divide by n. So that's MSE. And the last one is MAPE, mean absolute percentage error. So the way how it's calculated is for each of my records, I have to calculate the error, so the actual minus the predicted, take the absolute value and divide by the actual. That will tell me that that will allow me to calculate what percent is the error from the actual value. So this ratio essentially tells me that that in this case, for the car number I in the data set, my error is, let's say, 0.007, okay, which means 7%. So after that I have to add the relative absolute errors together, percentage errors together, divide by n, so I calculate the mean, and multiply it by 100%. So instead of 0.07, I'm going to get 7%. So I'm converting proportions into the percentages. Okay. So again, the meaning of the MAPE is it tells you on average what is the percent of error that you're making when using that specific regression model. Now obviously what I want is for my model to be precise, completely accurate, which means that the forecasted errors, forecasted values should be ideally exactly equal to the actual values. In this case, the differences, the errors, are going to be zeros, so my MAE is going to be 0, all errors are 0, so MSE is 0, all errors are zeros, MIPE is 0. So in ideal case, when my model is perfect, which never happens actually, all of these measures are going to be zeros. Well, and the worse the model becomes, the higher the values of MAE, MSE, and MAPE. So what am I saying here is really, let's say I calculate the MAE, MSE, and MAPE, and MAE gives me 1500. MSE gives me, let's say, 22,000. and MAP tells me 10%. Is that a good model? Is that a bad model? How do I know? Well, these numbers make sense only when you compare one model against another model. So by themselves, these values will not tell you much. But if I have model number 1 and model number 2, I can calculate for both of them all these measures and compare them. So whichever model gives me lower measures, lower MAE, MSE, and MAPE, that's the better model, because it predicts my numbers, my target, closer to the actual values. Simple as that. Alright, so to illustrate that, I'm going to bring up our example with Corolla. So I'm gonna run, let's see, this one, I believe, yeah, it's my regression tree right here. Okay, so I'm going to run through this code line by line. So first things first, of course, is we're reading the data. Okay, well, then I can go ahead and look at the structure of the data, always a good idea. So price is my target, predictors are age, mileage, fuel type, categorical predictor, as you can see, horsepower, whether or not the color is metallic, whether or not the car is automatic, the engine volume, number of doors, and weight. Okay, so first model that I'm going to run is my good old friend. It's actually right here. It's my regression tree. So just a reminder how this is done. I'm going to load the library rpart, and after that run this line, which says use the function rpart. Your target is the price, predictors are everything else, tilde dot. Data that we have to use is, well, the entire data set. So I'm not splitting right now for training and validation set, it's all training. And the method, instead of class, which means classification tree, I say ANOVA, which means regression tree. Okay, so I'm going to run this model, and after that I load the library rpart plot and plot my model. So the picture is right here. Okay, so again, all the final nodes, the at the bottom, leaves of the tree, they contain predictions. So for example, for the cars older than 33 months, but not older than 53, so between 53 and 33 months, with a mileage higher than 131,000, that's 10 to the third power, the estimated price for all these cars is going to be $8,400. Okay, so that's how we interpreted this tree, right? Okay, so well, and this is a scatter plot just to kind of show that, yeah, what we have is if the mileage is low, then the price tends to be higher, but as the mileage goes higher and higher, the price drops. So you can see that there is a dependency of price on the mileage. Anyhow, so I got my regression tree. So now I'm going to right here I'm going to calculate my measures. Okay, so as we discussed, my measures are going to be MAE, MSE, and MAP. These are my primary measures. Okay, but first I have to calculate predictions. So here what I'm doing is I'm calculate predicted, okay, predicted prices. All right, using my regression tree model. All right, so using the function predict, as we always do, I'm saying, hey, function predict, use my Corolla, this one right here, price regression tree model, and for the new data, use my old data, the same as I used to train the tree. Okay, so I'm going to run this line, and let's see, how many cars did I have in my original data set? 1,000 cars, right? Okay, so here I should have 1,000 predictions, right? Each car will generate a predicted price. Well, here is just all of my predictors. Well, in fact, yeah, I can see that already. 1,000, car number 1,000. The predicted price for that car was $94.91. 9400, I'm sorry, $91.17, right? Okay, in fact, I can see that they're all the same, right? At the very end of my data set. That's probably because they all belong to the same leaf of the tree. You can see that now the predictions changed, right? As I scroll through my predictions, they're all different, but the predicted values, they actually correspond to the leaves of my tree. That's why they're all the same, because all cars that will end up, let me show you the tree. Where is that? Right here. All cars that will end up, for example, in this node, they will get the same price predicted for them. That's why you don't see much difference between different prices. That just means that they all ended up here, for example. Okay, half of the cars, you can see that half of the cars, 50%, will be older than 53 months. Well, and older, of course, than 33 months, right? And in these cases, my price predictions for all these cars is going to be $9,491. That's why you see all these values the same. Okay, anyhow, now I have to calculate my measures, right? How well my model is doing. Well, for that we're going to use actually another library which we didn't use before. So I'm going to install forecast. Library is called forecast. Not surprisingly, right? Okay, so install, just like we always do, install dot packages, and the package is called forecast. Now I have to run it. Well, I already installed it, but they want to restart R prior to installing. No. Okay, and it's going to take some time actually. It will apparently download a whole lot of different libraries. Well, in my case, it's already will not be installed. Okay, so but in your case, when you run this line for the first time, don't be surprised if it will take you a minute or two, because the library calls other libraries, so it will download everything that it needs. So now I have my library forecast on this machine. I'm going to load the library forecast. Okay, all right, so library is loaded, and now what I'm going to do is calculate all these performance measures, how well or how badly my model is predicting the price. So I'm going to leave a comment here, calculate predictive performance measures. Okay, so for that I'm